Hello students of science. In this video we're going to talk about shifting equilibrium. In the last video we of course were talking about equilibrium constants. In this one we're going to talk about things that can change those equilibrium constants. So we need to learn about something called Le Chatelier's principle. That's the best French that I can do. It basically states that any equilibrium is going to adjust toward the reactants or toward the products if conditions are adjusted. I'm going to be labeling reactants for the most part in red here. Red reactant, blue product. Something that's going to shift it toward the reactants is going to be an arrow pointing more toward the left. Something that's going to shift it toward the products is going to be something pointed more to the right. So here we have our Haber process, or Haber process, depending upon if you want to pronounce German badly as well. So I have my initial concentration of both hydrogen and ammonia. However, if I add in nitrogen at this time, we are going to see an immediate change in all of the concentrations of all three of them. Hydrogen is going to drop, ammonia is going to increase, and that nitrogen after the initial addition is going to drop as well. Le Chatelier's principle talks about why. It basically states that you have any time there is a change in the status quo, there is going to be an opposing reaction in the responding system. If you put a stress on a system at equilibrium, the system is going to proceed in a direction that minimizes that stress. You do something, the system is going to try to undo it. And we're talking about changes in both pressure, reactant or product concentrations, and temperature. We're going to talk a little bit more about each one of those in depth, so you don't need to copy it down this moment. But anytime you do something, the system is going to try to minimize or almost undo what you just did. Let's first talk about changes in pressure. So the Haber or Haber process is when you take nitrogen and you add it to hydrogen gas and you make ammonia. Ammonia is very important for a fertilizer. So this process was actually incredibly important for saving literally billions of lives. So that's why we talk about it. But you have to look at it not in terms of the chemicals, but in terms of the number of moles. We start with 4 moles of gas, 1 of nitrogen and 3 of hydrogen, that's the ratio in a balanced equation, is going to make 2 moles. So think of it more in terms of my reactants are 4 moles, my products are 2 moles. Now, whenever I increase the pressure, I'm going to be shifting the reaction to the right. Why to the right? That's where there are fewer molecules. I have increased pressure. The system is going to try to undo that or minimize it by going to an area where there's less. Anytime I'm going to decrease the pressure, the system is going to shift more toward the left, more toward my reactants there. There's more molecules that take up more space. Whatever I do, the system's going to try to compensate for. So let's take a look. Here's my piston, and inside there I have nitrogen, hydrogen, and ammonia. The big ones are the ammonia. We'll see not a lot of ammonia in there, only 2 molecules compared to the rest there. However, when I increase pressure after it adjusts to equilibrium, you're going to see that I have a lot more ammonia around. My hydrogen gas has also decreased significantly. There's only 2 here where there's about 7 or 8 right there. My nitrogen gas is also down as well. So I've increased the pressure, so the system is responding by trying to go to an area where there is fewer moles of gas, so fewer pressure there. The system tries to undo it. So the genius of the Haber process is under pressure, you're able to make far more ammonia than you would otherwise. You have to put the system under pressure in order for this reaction to happen. Here's another one where I have calcium carbonate, calcium oxide, and carbon dioxide. When I increase pressure, the system's going to try to get that carbon dioxide out of there. The way it's going to be pulling that out, that carbon is going to go into that calcium carbonate. So my concentration, my amount of calcium carbonate has increased, my amount of calcium oxide has decreased correspondingly thanks to the reaction. But I increased pressure and it shifted towards something where there's going to be less of it there. That's Le Chatelier's principle. So this is going to shift the equilibrium position, but it is not going to affect the equilibrium constant, which is always going to be constant for a reaction at a specific temperature. The only reason that this is going to happen, well, you'd think that, oh, if it's shifting toward the products or the reactants, that should change the equilibrium constant. It doesn't, because really what's happening is I'm changing the volume, which is changing the concentrations. So the best thing about learning about equilibrium, nothing changes. Get it? All right, so let's talk about those changes in concentration. If I add a reactant, I'm going to shift an equation to the right. And if I add a product, I'm going to be shifting the equation to the left. It seems weird that these colors are opposites. The reactant is going to be pushing it more toward the right where things are bluer, and the product is going to be pushing it more toward the left where things are redder, but it makes sense. It's trying to undo whatever you've just done. I've taken a few yellow molecules out of here, and the whole reaction is going to shift to the left to sort of compensate for the fact that those are now missing. Now, you have to think of solids and pure liquids have essentially no pressure, so we do not include those in the equation when we are talking about the changes in concentration. So the new final concentrations are still going to have the same KEQ at that temperature because of the fact that when one has gone up, another one will have gone down. Let me give you another example here with our Haber process. So nitrogen, hydrogen makes ammonia. I'm adding in nitrogen right here. Well, when I'm increasing the amount of nitrogen, what's going to happen is more of the reaction is going to go to completion. So I'm going to get an increase in this ammonia to sort of compensate for the fact that that's going on there. If I'm pulling more of this out and making more ammonia, my hydrogen is actually going to decrease. So increasing nitrogen, making this one go up, will increase ammonia, which makes sense. The system is trying to compensate. However, I'm going to decrease hydrogen. This is the reason that the KEQ remains the same, because when one goes up, the other is going to go down to compensate for it. If I was to increase ammonia, that would increase both of them. So more of this means more of both of these as the system tries to pull that ammonia out. So when my nitrogen is added, those are the big blue ones right there, what's happening at the end is I have way less hydrogen and way more ammonia. So nitrogen went up, ammonia went up, hydrogen went down. If I change the temperature, that's going to have an effect as well. In a reversible reaction, one of them is always going to be exothermic. One of them is always going to give off heat, even if it's just a little, and in one direction, and in the other direction, it's going to be endothermic. It's going to pull out heat. Think of heat as a product in an exothermic reaction, and a reactant, what you start with in an endothermic reaction. So an exothermic reaction is giving off that heat. Think of it as a product. I'm going to be changing my equilibrium constant. So this is the one thing here that actually will change my KEQ. This is why it's very specific at that temperature. Here it is at my original temperature. If I heat it up, if I increase it, I'm going to get more of this reaction right here, so I'm going to get more product. So if you compare my original to my new equilibrium, it has shifted. I'm going to get more product in this particular example. So if I add heat to a reaction, that's going to shift it more toward the endothermic side of the reaction. If I'm going to remove heat, if I'm going to cool down this reaction vessel, I'm going to shift that reaction toward the exothermic side. So you add heat, it's going to try to pull it out with an endothermic reaction. If I take away heat, it's going to try to make up that heat with an exothermic reaction, sort of pushing it in the opposite direction. Now, whenever I'm removing a product, you have to think that the reaction is going to take place much more quickly. Why? Because it's like I'm constantly removing a product, so the system is constantly trying to replace that there. So it's pushed in that direction as it tries to reach equilibrium. It never can. When I'm making a precipitate, the reason those reactions are going to go to completion, you might say, is because I'm pulling that solid out. That solid is no longer interacting. The system is trying to compensate for that thing being gone. So you add a few drops of liquid to there, and the whole thing goes very quickly to completion as it tries to make more and more to make up the difference. If I was to produce a gas, that reaction is going to go almost perfectly to completion because that reaction is going to keep trying to push toward the product side to make up for the fact that I am losing that from the product side there. So anytime I'm giving off a gas and that gas is allowed to escape freely, the reaction is going to go almost always to completion because I am removing a product from there. So the reactants are going to be used up to make up for that difference. So Le Chatelier's principle is all about whenever I add something, there's going to be a consequence as the system tries to compensate. Here I have, you can almost think of this as reactants and products. They are at equilibrium because they are connected. If I'm to add something to one side, after the system completes, we are going to get it back at equilibrium. I added it to the left, I'm going to get more on the right. I had more reactants, now I'm going to get more products as the system tries to equilibrate. If I remove from one side, of course, the system is going to try to fix that as well by bringing down the level on the other side. That's Le Chatelier's principle. So let's sort of summarize this right here. I take a look at my stresses, either increasing or decreasing concentration, that's going to shift it. If I increase, that's going to go away from whatever I added. If I decrease, it's going to go toward that to make up for that. The reason when I'm increasing it, I need to use up that extra concentration, or I need to produce more to make up for what was removed. However, neither of those will have a change on my equilibrium constant, KEQ. If I increase or decrease the pressure, increasing it is going to push it toward fewer moles of gas. It's trying to make up for that lack of space. If I decrease the pressure, it's going to make more of it. There, it's trying to make up that space. So whenever I have a pressure increase, that's going to be a volume decrease, and a pressure decrease is going to be a volume increase. So it's trying to make up those differences there. Neither one of those, though, has an effect on the KEQ. Temperature. Remember, if I increase the temperature, if I heat up a system, I'm going to go away from that. So I'm going to have an endothermic reaction. If I decrease the temperature, an exothermic reaction is now going to be favored. So think of it as the extra heat needs to be used up, or you need to make that heat to make up for the loss. These are the ones that actually will have an effect on the equilibrium constant. And finally, a catalyst. Remember, catalyst doesn't change what you start with or what you end with. All it changes is how quickly you get there. Think of it as like taking an airplane from here to Disney World. You could walk there. Catalyst just makes it happen faster, but it doesn't change where you start or where you end. So there is no shift. The forward and reverse reactions are both going to take place, but they're both going to be faster and they're going to cancel out. So in the end, no effect on the KEQ. The only thing that actually can change your equilibrium constant is temperature, and that's why whenever we have an equilibrium constant, it's very specific for that reaction at that particular temperature.